Hello students, in this module, which is part 4 in our series on differential equations, I'm going to tell you how to use the method of eigenfunction expansions, or what is also known as the finite Fourier transform, to solve linear differential equations, both ODEs and PDEs. Okay. Now, before I do that, I will first try to solve a PDE, a partial differential equation, using the method of what is called the separation of variables. I will tell you that the method of separation of variables is very intimately connected to the notion of eigenfunction expansion and finite Fourier transform. So it is the same thing but slightly packaged differently. Okay, so let us consider. So we'll use separation of variables. To solve this PDE. Okay, now x belongs to 0 and L. Okay, the domain is L and time t greater than 0. Okay, so this is a second order differential equation in x and first order in time. So you need two boundary conditions and one initial condition, okay, to solve this. So the two boundary conditions are t at x is equal to 0 at all times is equal to ta excuse me, and t at x is equal to L at all times t greater than 0, that is also ta. Okay, now this is for all t greater than 0. Okay, the initial condition is t at all x at time t equal to 0 is some t naught of x. Okay, now so initially there is some temperature distribution in a given a bar, rectangular bar, let's say, and this is the x direction. This is x is equal to 0. This is x is equal to L. This is the unsteady heat conduction equation. Okay, that you must have seen in courses on transport phenomena or heat transfer, right? Okay, so now the way the problem has been formulated, so we have to find, so what is the goal? The goal is to find how the temperature distribution evolves as a function of x and time. Okay, as formulated or as provided, the problem has inhomogeneous boundary conditions. Okay, right. So now it is easy to change the boundary conditions to homogeneous by redefining the temperature as T minus Ta. So instead of T of xt, we are now going to solve for y of xt. Okay, so the governing equations will become d squared y by dx partial squared y by partial x squared is 1 over alpha. Alpha is the thermal diffusivity. Okay, times partial y partial t. Now the initial and boundary conditions are y at x is equal to 0 at all times is equal to 0. Y at x is equal to L at all times is 0. These are the boundary conditions. And y at x t is equal to 0 is t naught of x minus ta. Let's just call this y naught of x. This quantity is called y naught of x, just for simplicity. Okay, now the notion of separation of variables is as follows. Here we say that y is a function of two variables, x and time. So we would like to write it as a product of two functions, of which the function x is a function only of capital X is only a function of space, and the function capital theta is only a function of time. So this is in some sense a postulate or a guess. This is what we want our solution to look like. Okay, so I substitute this back in the PDE. So I'll get partial by partial x squared x of x theta of t is equal to 1 over alpha partial by partial t x of x theta of t. Okay, now theta is a function only of time, so in this expression I can pull this out. So this is theta of time partial squared, this should be partial squared, I'm sorry, x by partial x squared is 1 over alpha. Likewise here x is a function only of space, so I can write this as partial theta by partial t. Okay, now I'm going to divide the entire equation by this product theta of t times x of x, which will give 1 over x partial squared x by partial x squared is 1 over alpha 1 over theta partial theta by partial t. Now if you look at this differential equation, the left side is a function only of x. Why? Because capital X is a function only of x, and its second derivative will also be a function only of x, whereas the right side is a function only of t, for the same reason that theta is a function of time and its first derivative will be a function of time. So if this equation has to hold true, then we require that both sides must equal a constant. Okay, so that is the idea in separation of variables. So you write 1 over x. Now you don't have to write the partials any longer, because capital X is a function only of small x, so I can write this as an ordinary derivative. Similarly 1 over alpha times 1 over theta, and the partial derivative can be written as an ordinary derivative because theta is a function only of time. So each has to be equal to a constant. Let's call that constant minus lambda. Okay, now the boundary conditions. So we had y at x is equal to 0 t, that is the same as x at x is equal to 0 times theta of t is equal to 0, and that means that this is true for all times. So this means that x of x is equal to 0 is 0. The other boundary condition will give that y at x is equal to L t is 0, will similarly give x at x is equal to capital L at all times is 0. Okay, the initial condition will be x of x times theta at time t equal to 0 is equal to y naught of x. Okay, that is the initial condition. Okay, now let's look at this equation. Each of this, now this must be equal to minus lambda. Okay, if we use that, is equal to minus lambda, or d squared capital X by d small x squared plus lambda capital X is 0, and subject to x of 0 is 0, x of L is 0. Okay, now obviously this is a homogeneous equation with homogeneous boundary conditions, so there is always a homogeneous solution capital X being 0 is always a solution that satisfies both the differential equation and the boundary conditions. But that is only what is called the trivial solution. Okay. So for non-trivial solution, we have to write capital X of X in general is C1. The two linearly independent solutions are sine and cosine. Sine of root lambda x plus C2 cos of root lambda x. Okay. At x is equal to 0, x of x is equal to 0 is 0. This means that C1 times 0 plus C2 times 1 is 0, or C2 is 0. Okay. At x is equal to L, x of x is equal to capital L is equal to 0, which means cos root lambda, sine root lambda L is 0, or root lambda L must be is equal to plus or minus n pi, where n goes from 0, 1, 2. Okay. So but n is 0 is not important, because that will give you the trivial solution, because sine 0 is 0. So in general, for non-trivial solution, we require, suppose if I square this equation, lambda n L squared is equal to n squared pi squared, or lambda n is equal to n squared pi squared by L squared. Okay. So the solutions, therefore, to this homogeneous equation, there are many solutions, right? Because this is a homogeneous equation, we found many non-trivial solutions depending on what lambda is. For each lambda, you get a solution of the form xn of x is equal to sine root lambda n x is equal to sine n pi x. Okay. And because we have squared here, n can take only the value, so there is no need for plus or minus n. Okay, there is no need for plus or minus n, as we have seen before also, because sine of minus n is minus sine of n, so n can be safely taken to be 1, 2, 3, 4 and so on. There is no need to have negative values, because the eigenfunction, the functions that you get, are basically a negative of what we have already included. Now what we have solved in this separation of variable problem, sort of inadvertently, so to speak, is an eigenvalue problem, because this is an eigenvalue problem, a differential eigenvalue problem, and these are the eigenvalues, lambda n, these are the eigenvalues. Okay, so the separation of variable way of solving PDEs, linear partial differential equations, also involves a solution of an eigenvalue problem. Although we do it in a sort of indirect manner, we don't directly expand the unknown in terms of eigenfunctions. Okay, so but on the other hand, we sort of get the eigenvalue problem from the governing equations itself, and then we say that, well, there are many solutions, so each solution, these are eigenfunctions. Okay, so, and note that signs are orthonormal, sine n pi x by L, sine m pi x by L dx is equal to 0 if m is not equal to n. They are orthogonal functions. Okay, so this is how we get right? Even in the separation of variable method of solving partial differential equations, we do get to solve an eigenvalue problem. Okay, now we have to solve for the initial condition. Okay, first of all, we write x of x is summation n is equal to 1 to infinity. Okay, so we can write specifically y of xt is a product of, note that y of xt is a product of x of x and theta of t, right? Now we have not solved for theta of t yet, so let's solve that as well. So if you solve theta of t here, let me just solve it here, then you will find that d theta dt is minus alpha lambda t. Okay, and lambda is n squared pi squared by l squared, so theta of t is theta of 0 times e to the minus alpha, okay, which is lambda n t. Okay, so this is, so if you write y as a product of theta of t times x of x, but then x of x is just not one solution, there are many solutions, so you have to add them all up. This is where the notion of eigenfunction expansion comes in an indirect manner. Okay, times, now this is, let's say, for each value of these eigenfunctions, you have to have this theta of 0 can be written as some a n at time t equal to 0 times some constant a n times sine root lambda n x times e to the minus alpha lambda n t. Now we have to solve for these constants, but we have not used the initial condition. So in order to solve this constant, we have to use the initial condition. Okay, in order to solve these constants, you have to use the initial condition. The initial condition is y of x at t equal to 0 is y naught of x, that is equal to summation n is equal to 1 to infinity a n sine root lambda n x times 1, because this is evaluated at t equal to 0. Now how do you find ans? Ans can be found, this is like a Fourier expansion of y naught of x in terms of the eigenfunction sine lambda n x. So the Fourier coefficients can be found using orthonormality of signs. Once ans are known, then the solution is known, because the ans are determined. The y naught of x is a known function. Sorry about this. This is the known initial condition. So you find ans. Once you find ans, you substitute them, and then you get the solution to this problem. Okay, and what are lambda n's? Lambda n's we know, n squared pi squared by l squared. Okay, that is lambda n. Okay, this is how we solve the problem using separation of variables. But then note that even in separation of variables, we had to use the notion of an eigenfunction expansion, although you do it in a sort of indirect way, but it has to be used. Okay, so we will rather emphasize that we can straight away solve such problems using the method of eigenfunction expansions, or some books call it finite Fourier transform. Or more generally, this is a more appropriate sort of name for such techniques. Okay, let's consider a self-adjoint second order operator. L, okay, and with some set of BCs such that it is self-adjoint. The eigenvalue problem for this operator is L phi is minus lambda rho of x times phi. Okay, in general rho of x need not be 1, and then there are some boundary conditions operating on phi is 0. Okay, so because it's a self-adjoint operator, this eigenvalue problem has real eigenvalues, and you have an infinite set of real eigenvalues, and for corresponding to each distinct eigenvalue, for each distinct eigenvalue you have an eigenfunction phi n of x, and this phi n, phi m, they are orthogonal. Okay, and we can also make the set orthonormal. In general, when you have rho of x here in the eigenvalue problem, if it is 1, that's fine. If it is not, if it's some other function, let's say x or something, the definition of inner product will have rho of x. Okay, is delta n. This is the meaning of the inner product. This is sometimes called the weighting function. Okay, now if you get such eigenfunctions, then any function f of x in that domain, let's say a, b, can be expanded in terms of I is equal to 1 to infinity ci phi I of x, where phi i's are these eigenfunctions. Okay, now how do you find ci's? Use orthonormality as usual. Okay, so ci is nothing but integral a to b rho of x f of x phi I of x dx. Okay, this is as simple as that. So you can expand any function in the domain in terms of these eigenfunctions. So this is, you can think of it as a generalized Fourier series if you wish. Okay, or if you think of eigenfunction expansions as a general method, Fourier series is one example. So some people call it a generalized Fourier series. Okay, so if I substitute this ci back in here, so I'll get f of x is equal to summation I is equal to 1 to infinity. Instead of ci, I'm going to have this, but I should not use x twice in an expression. This is integrated over. I use a dummy variable, rho of z f of z phi I of z dz, then phi j of x. Okay, so this is the general expression for a function expressed in terms of eigenfunctions. Okay, so these are the coefficients of expansion similar to the Fourier coefficients. Okay, so these are in some sense the finite Fourier transform of f of x, the coefficients, and this is the inverse transform. Once you know the coefficients, then how to find the function. Once you know the function, how to find the coefficients. This is in some sense similar to the pair Fourier transform pair that we wrote, but this is for discrete eigenfunction expansions. So the same information is contained in either in the function f of x or in the expansion coefficients ci's. Okay, they have the same information. It is just saying the same information in different bases in some sense. Okay, alright, so now once we understand this, we can solve ODEs, boundary value problems involving ODEs. We will come to PDEs in the next segment. Boundary value problems or BVPs involving ODEs. Okay, so d squared y, let's say dx squared minus u squared y is equal to minus f of x. Let's say this is the problem. X is between 0 and L, let's say y of 0 is 0, y of L is 0. Okay. Now let's consider the operator L1 as d squared by dx squared. So this equation can be written as L1y minus u squared y is equal to minus f of x. Okay. Now solve the eigen. This is a Hermitian operator. We know that. This is a self-adjoint operator. Solve the eigenvalue problem of L1. So L1 phi I is equal to minus lambda I phi I. Okay. Again subject to the homogeneous conditions. Phi of 0 is 0. Phi I of L is 0. Okay. Right. So if you solve this, you will get the usual lambda n as n squared pi squared by L squared. N is equal to 1, 2 and so on. And phi n of x is root 2 by L sine. Okay, these are the eigenfunctions. So we have gotten. So we have now L1y minus u squared y is equal to minus f of x. We want to solve this. So how do you do this? Using the finite Fourier transform method, multiply the entire equation by phi n of x and integrate between the domain 0 and L. Okay, if you do this, you get 0 to L phi n L1 operating on y dx minus u squared 0 to L phi n of x y equal to minus 0 to L f of x phi n of x dx. Now by definition, what is this? This is a function and you are multiplying it by phi and integrating. Of course there is dx all around. In case if I forget, please add them. Okay, what is this term? This is nothing but, if you were to expand the function y of x in terms of phi n, it will have coefficients of expansion yn. Similarly, this is, if you add a function f of x and if you expanded it as f of x is summation fn phi n, then what are fn's? That will be given by here. This is fn, right? So if you understand this, therefore we can rewrite this equation. I'm sorry about this. Now the operator is before I rewrite this equation, this operator is self-adjoint. That means that this term is the same as integral 0 to L y L1 of phi n dx. Okay, this is the meaning of self-adjoint operator. Okay, meaning comma LV is equal to LU V, right? That's the same thing here. Okay, if it is self-adjoint, L1 we know is self-adjoint, then it can be written like this. But L phi 1 is nothing but L1 phi 1 is nothing but lambda. So L1 phi n is lambda n phi n. So if I go to the next page, this equation becomes 0 to L, right? This is nothing but y, there has to be a minus n because that's how we solve the minus eigenvalue problem. Okay, so let me continue here itself. So this equation becomes therefore 0 to L y minus lambda n phi n dx. Okay, now what is this? This is nothing but 0 to L minus lambda n y of x phi n of x dx. But this quantity is nothing but, if you were to have y of x and if you wanted to expand it in this basis, the coefficients will be yn, because y of x phi n of x, these are the eigenfunctions. 0 to L is just yn. Okay, so we can rewrite this equation as minus lambda n yn minus u squared yn is equal to minus fn, or yn is equal to fn by lambda n plus u squared. Okay, therefore y of x is nothing but summation n is equal to 1 to infinity yn phi n of x. That's nothing but n is equal to 1 to infinity fn by lambda n plus u squared times phi n of x. Okay, if you are to write it in full form, y of x is 2 by L summation n is equal to 1 to infinity. If you want to write what is fn and so on, so this is 1 by and u squared plus what is lambda n squared pi squared by L squared. What is fn? It's nothing but 0 to L f of z. I'm using a dummy variable z, sine n pi z by L dz, operating on sine. Okay, this is the exact solution to this inhomogeneous problem that we started off with. Okay, so this is how one solves such ordinary differential equations using finite Fourier transform or using the method of eigenfunction expansions. The final solution will be in the form of a series or summation of eigenfunctions. In principle, they go all the way up to infinity. In practice, you truncate it at some n as per the requirement of your accuracy. Okay, so in the next module we will start with the solution of linear PDEs using the same eigenfunction expansion method or the finite Fourier transform method. Thank you.